In the closing decades of the 19th century, physics stood at what many believed was its final moment of triumph. The natural world seemed decoded. Motion, heat, light, electricity, and magnetism were all described by elegant mathematical laws. Newton's mechanics had explained the movement of planets and projectiles with astonishing precision. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single theoretical framework. To many leading scientists of the time, the universe appeared to be a perfectly constructed machine, governed by continuous laws that left little room for mystery. It was widely believed that future physicists would merely refine measurements and calculate values to greater decimal accuracy. Yet beneath this confidence, subtle cracks were beginning to appear. Laboratories across Europe were producing experimental results that quietly resisted explanation. These were not dramatic failures, but small discrepancies, often dismissed as experimental error or incomplete data. However, as instruments became more precise, these inconsistencies refused to disappear. One of the earliest warning signs came from the study of heat and radiation. Physicists had long been interested in understanding how hot objects glow, how they emit light, and how the color and intensity of that light change with temperature. According to classical physics, energy flowed smoothly and continuously, like water from a tap. This assumption had worked well for many mechanical systems, but when applied to radiation, it began to produce troubling predictions. The concept of a blackbody became central to this investigation. A blackbody is an idealized object that absorbs all incoming radiation and re-emits energy solely based on its temperature. Experimentalists could closely approximate such objects using heated cavities with small openings. When scientists measured the radiation emitted from these cavities, they obtained precise curves showing how intensity varied with wavelength. These curves were remarkably consistent and reproducible. The challenge was not experimental uncertainty, but theoretical explanation. Classical physics attempted to describe these curves using established principles, yet every attempt either partially failed or completely broke down. One classical approach, rooted in thermodynamics, worked reasonably well at low frequencies. Another, based on electromagnetic theory and statistical mechanics, seemed promising at high frequencies. However, when these ideas were combined, they led to a catastrophic prediction. The theory suggested that as wavelength decreased, the energy emitted should increase without limit. This implied that a hot object should emit infinite energy at very short wavelengths, an obviously impossible result. This failure became known as the ultraviolet catastrophe, not because it involved violence, but because it represented a total collapse of classical reasoning in the ultraviolet region of spectrum. At first, many physicists hoped that the problem lay not in the theory, but in experimental imperfections or incomplete mathematical treatments. Confidence in classical physics was so strong that the idea of a fundamental breakdown seemed unthinkable. After all, the same theoretical framework had successfully explained planetary motion, bridges, steam engines, and telegraph systems. To question it was to question the intellectual foundation of an entire century of scientific progress. Yet, as more data accumulated, it became increasingly difficult to ignore the mismatch between theory and reality. This crisis extended beyond radiation. The behavior of atoms themselves raised troubling questions. Classical electrodynamics predicted that electrons orbiting a nucleus should continuously radiate energy and spiral inward, leading to atomic collapse. Matter, according to classical logic, should be unstable, and yet atoms clearly existed and remained stable over time. Once again, theory and observation stood in direct conflict. Attempts to patch the theory only added complexity without resolving the core issue. Another troubling area involved specific heat capacities of solids. Classical physics predicted that all solids should store heat in the same way at a given temperature. Experiments showed otherwise. At low temperatures, measured heat capacities dropped sharply, deviating from classical expectations. This was not a minor error, but a systematic failure that appeared across many materials. The more carefully scientists measured, the clearer it became that something fundamental was missing. Despite these growing problems, the dominant attitude remained optimistic. Many physicists believed that these were temporary puzzles, not signs of a deeper revolution. Some even argued that physics was nearing its end, famously suggesting that there was nothing left to discover except more precise measurements. This mindset made it difficult for radical ideas to gain acceptance. The authority of classical physics acted as both a guide and a barrier, shaping how scientists interpreted new evidence. The cultural context of the time also played a role. The late 19th century was an era of industrial success and technological expansion. Railways, factories, and electrical grids transformed society, all built upon classical physical principles. This success reinforced the belief that the existing framework was fundamentally correct. When theory failed, the instinct was to blame experimental error or mathematical approximation rather than the underlying assumptions themselves. Yet science advances not only through confidence, but through confrontation with failure. The crisis in classical physics was not a single dramatic moment, but a slow accumulation of unresolved questions. Each anomaly weakened the belief in continuity and determinism that had defined classical thought. The idea that nature might operate in discrete steps, or that certainty might be replaced by probability, lay far outside the accepted world view. Still, the evidence was pushing in that direction. Young physicists entering the field at the turn of the century encountered a strange landscape. On the surface, physics appeared complete and elegant. Beneath it, unresolved contradictions waited patiently. Some researchers chose safe paths, refining existing theories. Others, often reluctantly, began to consider that the problem might not be with the details, but with the foundation itself. This tension created an atmosphere of quiet unease, a sense that something profound was about to change, even if no one could yet say how. The crisis of classical physics was not the result of failure in effort or intelligence. It arose precisely because physicists had pushed their theories to their limits. By demanding that equations match reality with absolute precision, they exposed the boundaries of old ideas. The same mathematical rigor that had built classical physics now revealed where it stopped working. This moment was not an end but a turning point, where the strength of science lay in its willingness to abandon certainty in the face of evidence. As the 19th century gave way to the 20th, physics stood at a crossroads. The old laws still worked brilliantly in everyday situations, but they could no longer claim universal authority. The stage was set for a new way of thinking, one that would challenge intuition, redefine energy and matter, and reshape humanity's understanding of the universe. The crisis of classical physics was not merely a technical problem. It was a philosophical shock, signaling that nature was far stranger than anyone had imagined. As the 20th century approached, the unresolved tensions within physics grew impossible to ignore. What made the situation especially unsettling was that classical physics continued to work extraordinarily well in everyday life. Engineers could design machines with confidence, Astronomers could predict planetary motions centuries in advance, and new technologies kept emerging from old equations. This dual reality created a deep intellectual discomfort. How could a theory be so successful and yet so fundamentally wrong in certain domains? The answer was not immediately clear, and for many scientists, this contradiction felt almost personal, as if nature itself were betraying the rules they trusted. The problem was not simply that classical physics produced incorrect numbers. It failed in a more profound way. It offered predictions that violated physical reality. Infinite energy, unstable matter, and universal behaviors that did not exist in nature were not small errors that could be corrected by better instruments. They were signs that the assumptions underlying the theory no longer matched the structure of the physical world. Energy, long treated as a smooth and continuous quantity, was beginning to show signs of granularity. Matter, once thought to be predictable and orderly at all scales, revealed unpredictable behavior when examined closely. Many physicists attempted to rescue classical ideas by introducing corrective factors. They adjusted equations, added constraints, and developed hybrid models that worked in limited cases. These efforts often succeeded temporarily, giving the illusion that the crisis could be managed without radical change. However, each fix created new inconsistencies elsewhere. The theory was becoming increasingly complicated, less elegant, and more fragmented. What had once been a unified and beautiful framework began to resemble a collection of patches holding together a structure that no longer fit its purpose. The emotional dimension of this crisis is often overlooked. For scientists trained in the classical tradition, abandoning long-held beliefs was not easy. Classical physics was more than a set of equations. It was a world view. It assumed that nature was deterministic, that knowing the present precisely meant knowing the future completely. It assumed continuity, causality, and objective reality independent of observation. These ideas aligned closely with common sense and philosophical traditions stretching back centuries. To question them felt like stepping into intellectual chaos. Yet younger researchers, less emotionally attached to classical certainty, were more open to questioning fundamentals. They encountered contradictions not as threats but as challenges. For them, the crisis represented opportunity rather than failure. This generational shift played a subtle but crucial role. Science, after all, does not advance solely through data and equations, but through human willingness to rethink assumptions. The growing gap between observation and theory created space for new ideas to emerge. Another factor that intensified the crisis was the increasing precision of experiments. Advances in instrumentation allowed scientists to probe nature at smaller scales and higher energies than ever before. These experiments did not merely refine existing knowledge. They exposed behaviors that classical physics could not anticipate. The more carefully nature was examined, the stranger it appeared. Precision, once the ally of classical theory, became its greatest adversary. At the heart of the crisis lay a fundamental question: is nature truly continuous, or is continuity an illusion created by human perception? Classical physics assumed smoothness because it matched everyday experience. We see objects move along continuous paths, hear sound as a flowing wave, and feel heat as a gradual sensation. But these experiences occur at scales far removed from atoms and radiation. When scientists finally reached those scales, continuity began to break down. Nature appeared to operate in jumps rather than flows, thresholds rather than gradients. This realization challenged not only physics, but philosophy. If energy and matter behaved discretely, What did that mean for causality and predictability? If equations could only describe probabilities rather than certainties, how should science define explanation itself? These questions lingered in the background long before clear answers emerged. The crisis of classical physics thus became a crisis of understanding, forcing scientists to confront the limits of human intuition. Importantly, classical physics was not discarded. Its laws remained valid in many contexts and still form the backbone of engineering and macroscopic science. The crisis did not destroy classical physics. It revealed its domain of applicability. This distinction was crucial. The problem was not that classical physics was wrong, but that it was incomplete. Recognizing this required humility and acceptance that even the most successful theories are provisional. The transition away from classical certainty did not happen overnight. It unfolded gradually through cautious steps and reluctant admissions. Many physicists adopted new ideas only when they became unavoidable. Even then, acceptance was often partial, mixed with discomfort and skepticism. The language of physics itself struggled to adapt. Old terms were stretched to describe new phenomena, sometimes obscuring their true meaning. The crisis also reshaped how scientists viewed the role of theory. Rather than being seen as a final description of reality, theories began to be understood as models that approximate nature under specific conditions. This shift marked a profound change in scientific thinking. It acknowledged that human knowledge is limited and that nature does not conform to our expectations simply because they are elegant or intuitive. By the early years of the 20th century, it was clear that a new framework was needed. The cracks in classical physics had grown into fractures, and through them, glimpses of a deeper structure of reality were emerging. The crisis was no longer a source of embarrassment, but a catalyst for creativity. It forced physicists to ask not how to preserve old ideas, but how to understand nature on its own terms. In retrospect, the crisis of classical physics stands as one of the most productive failures in the history of science. It demonstrated that progress often begins where certainty ends. By exposing the limits of established knowledge, it opened the door to concepts that would redefine energy, matter, space, and time. The discomfort, resistance, and confusion of that era were not signs of weakness, but evidence of science doing what it does best, evolving in response to reality. This period reminds us that scientific revolutions do not begin with answers, but with questions that refuse to go away. The inability of classical physics to explain certain phenomena was not a dead end but an invitation. It invited thinkers to imagine that the universe might be structured in ways far stranger and more subtle than previously believed. From this invitation emerged quantum physics, a new language of nature born directly from the crisis that classical certainty could not survive. Toward the end of the 19th century, physicists were increasingly fascinated by a deceptively simple question: how does a hot object emit light? At first glance, the glow of heated metal or the light from the sun seemed ordinary, even familiar. Yet, when scientists attempted to describe this behavior with mathematical precision, they encountered one of the most profound problems in the history of physics. This problem did not arise from speculative theory, but from careful experiments that produced clear, repeatable results. The difficulty lay entirely in explaining those results using the well-established laws of classical physics. To study thermal radiation under controlled conditions, physicists introduced the concept of an idealized object that absorbs all incoming radiation and emits energy solely as a function of its temperature. This object became known as a blackbody. While no perfect blackbody exists in nature, researchers could approximate one using a hollow cavity with thick walls and a tiny hole. Radiation entering the hole would bounce around inside, becoming completely absorbed. The radiation escaping from the hole, therefore, represented pure thermal radiation determined only by the temperature of the cavity. This setup allowed scientists to isolate the phenomenon and measure it with remarkable accuracy. When these experiments were conducted, a clear pattern emerged. As the temperature of the blackbody increased, the intensity of emitted radiation increased, and the peak of the emission shifted toward shorter wavelengths. At lower temperatures, most radiation was emitted in the infrared. At higher temperatures, visible light appeared, and eventually ultraviolet radiation became significant. The shape of the radiation curve was smooth and consistent, and it could be reproduced in laboratories around the world. There was no confusion about what nature was doing. The confusion arose when physicists tried to explain why. Classical physics approached this problem using two powerful tools: thermodynamics and electromagnetism. Early formulas based on thermodynamics described the radiation reasonably well at longer wavelengths. These results gave physicists confidence that they were on the right track. Later, more sophisticated approaches combined Maxwell's electromagnetic theory with statistical mechanics, treating radiation as standing electromagnetic waves inside the cavity. Each possible wave mode was assumed to carry energy, and statistical methods were used to calculate how energy would be distributed among these modes at a given temperature. At first, this approach seemed promising. It relied on well-tested ideas and elegant mathematics. However, as calculations were extended to shorter wavelengths, the predictions became increasingly troubling. The theory suggested that there were infinitely many possible wave modes at very high frequencies, and each mode, on average, should carry a certain amount of energy. When these contributions were added together, the total energy diverged. According to classical theory, a blackbody should emit an infinite amount of energy, with most of it concentrated at very short wavelengths. This result was not merely inaccurate, it was physically impossible. No object could emit infinite energy. Moreover, experiments showed the exact opposite behavior. At very short wavelengths, the intensity of radiation dropped sharply instead of rising without bound. The discrepancy between theory and experiment grew worse the more carefully scientists examined it. This dramatic failure of classical prediction became known as the ultraviolet catastrophe, a term that captured both the mathematical breakdown and the conceptual shock it produced. The significance of this problem cannot be overstated. Classical physics had always been grounded in continuity. Energy was assumed to vary smoothly, without abrupt jumps or limits. The ultraviolet catastrophe directly challenged this assumption. It suggested that applying classical ideas to radiation at small scales led to absurd conclusions, yet abandoning continuity felt unthinkable. It was deeply woven into the fabric of physics and aligned perfectly with everyday experience. For a time, physicists hoped that the catastrophe could be avoided by refining the theory. Some suggested that new boundary conditions or improved mathematical treatments might resolve the issue. Others believed that the problem lay in unrealistic assumptions about the cavity or the behavior of matter at high frequencies. These efforts produced partial successes, but failed to address the core contradiction. The divergence at short wavelengths stubbornly remained. The blackbody radiation problem was especially unsettling because it arose in a domain where classical physics should have been strongest. Radiation inside a cavity could be described using Maxwell's equations, among the most successful equations ever written. Statistical mechanics, though still developing, had already explained many thermal phenomena with great accuracy. The failure of these tools in such a fundamental problem suggested that something far more radical was required. What made the situation even more puzzling was that different classical formulas worked in different regions of the spectrum. One equation accurately described low-frequency radiation, while another matched experimental results at high frequencies when adjusted empirically. There was no single classical expression that worked everywhere. This patchwork success hinted that the underlying assumptions were flawed. Nature seemed to be switching rules depending on scale, something classical physics was not designed to handle. The Blackbody problem also exposed a deeper issue about how energy interacts with matter. Classical theory assumed that matter could absorb and emit energy continuously, exchanging arbitrarily small amounts. The experimental data, however, suggested a natural suppression of high-frequency radiation, as if some mechanism were preventing energy from flowing freely into those modes. This behavior had no explanation within classical theory, which allowed energy to spread endlessly across all possible frequencies. As physicists wrestled with this puzzle, the atmosphere in the scientific community grew tense. This was not a marginal anomaly, but a central problem connected to heat, light, and electromagnetism. If classical physics failed here, where else might it fail? The confidence that physics was nearing completion began to erode. The Blackbody radiation problem became a symbol of deeper unresolved tensions within the field. The problem also had philosophical implications. Classical physics was built on determinism and predictability. Given complete information about a system, its future behavior could, in principle, be calculated exactly. The divergence in Blackbody radiation suggested that classical assumptions led to nonsensical results when pushed to their limits. This raised uncomfortable questions about whether nature truly followed continuous, deterministic laws at all scales. Importantly, the Blackbody problem did not point clearly toward its solution. It revealed a failure, but offered no obvious alternative. The data did not demand a specific new theory. They merely insisted that the old one was incomplete. This made the situation particularly frustrating. Physicists knew something was wrong, but could not yet articulate what needed to change. Experimentalists continued refining their measurements, producing ever more precise radiation curves. These curves became a kind of mirror held up to theory, reflecting its inadequacies with increasing clarity. The problem could no longer be ignored or dismissed. Any comprehensive theory of matter and radiation would have to account for these results exactly. The Blackbody radiation problem thus occupied a unique position at the turn of the century. It was both highly technical and deeply conceptual. On the surface, it concerned the distribution of light emitted by hot objects. Beneath that surface, it challenged assumptions about energy, matter, and the nature of physical law. It forced physicists to confront the possibility that continuity, one of their most trusted principles, might not be fundamental after all. This tension created the conditions for a breakthrough. The problem was ripe for a new idea, one that would not merely adjust classical theory, but replace one of its core assumptions. The stage was set for a solution that would emerge not from bold speculation, but from a desperate attempt to make theory agree with experiment. The Blackbody radiation problem, stubborn and unforgiving, demanded a radical response, even if its consequences were not yet fully understood. By the time the 19th century came to an end, it was clear that the Blackbody problem was more than a technical detail. It was a warning sign that physics was approaching the limits of its classical foundations. The glow of heated objects, so familiar and seemingly simple, had revealed a deep mystery at the heart of nature. That mystery would soon force a transformation in the way scientists understood energy and reality itself. As the new century began, the Blackbody radiation problem continued to dominate discussions. Among theoretical physicists, what made it especially troubling was its clarity. Unlike many scientific puzzles clouded by uncertain data, this problem stood on firm experimental ground. The radiation curves were precise, consistent, and universally reproducible. Nature was speaking clearly, yet the mathematical language of classical physics could not translate what was being said. This gap between observation and explanation became impossible to ignore, and it steadily undermined confidence in the completeness of existing theory. The failure of classical approaches forced physicists to re-examine assumptions that had long been taken for granted. One such assumption was the idea that matter and radiation could exchange energy in arbitrarily small amounts. In classical thinking, there was no minimum unit of energy. A vibrating charge could emit radiation continuously, losing energy smoothly over time. The Blackbody data, however, suggested that this smooth exchange did not occur. High-frequency radiation was somehow suppressed, as if nature imposed a cost on producing it. This behavior hinted at a hidden rule, one that classical theory could not express. Attempts to resolve the problem without abandoning continuity grew increasingly strained. Some physicists proposed that interactions between matter and radiation might weaken at high frequencies. Others suggested that unknown properties of materials or experimental limitations were responsible for the discrepancy. These ideas were explored seriously, but none could reproduce the full radiation curve without contradiction. The more complex the classical explanations became, the less convincing they appeared. The simplicity of the experimental data stood in stark contrast to the growing complexity of theoretical excuses. The Blackbody problem also exposed limitations in statistical mechanics as it was then understood. The classical application of statistics assumed that energy would naturally distribute itself equally among all available modes. This principle, known as energy equipartition, had worked well for many systems. Yet when applied to radiation, it led directly to the ultraviolet catastrophe. The failure of equipartition in this context suggested that the statistical rules governing microscopic systems were incomplete or misapplied. This realization struck at the heart of how physicists connected microscopic behavior to macroscopic observations. Another unsettling aspect was that the problem appeared universal. It did not depend on the specific material of the cavity walls or the details of the experimental setup. The same radiation curve emerged regardless of the substances used, provided thermal equilibrium was achieved. This universality implied that the issue was not a property of matter, but a fundamental feature of nature itself. Any successful explanation would have to be equally universal, applying to all forms of matter and radiation. The psychological pressure on the physics community grew steadily. For decades, classical physics had offered not only answers but confidence. It had taught scientists what kinds of questions were reasonable to ask and what forms answers should take. The Blackbody radiation problem disrupted this intellectual comfort. It suggested that the universe might not conform to human expectations of smoothness and continuity. Accepting this possibility required a willingness to let go of deeply rooted intuitions. In this climate of uncertainty, a subtle shift occurred in how physicists evaluated new ideas. Mathematical consistency and agreement with experiment began to outweigh philosophical comfort. The question was no longer whether a theory aligned with classical intuition, but whether it accurately described reality. This change in attitude was crucial. It prepared the scientific community, even if unconsciously, for a solution that would initially seem unnatural and even absurd. The eventual resolution of the Blackbody problem did not emerge from a grand philosophical vision, but from a pragmatic decision. In attempting to fit experimental data, a new assumption was introduced that restricted how energy could be exchanged between matter and radiation. This assumption broke with classical continuity, but succeeded where all previous attempts had failed. At first, it was treated as a mathematical device rather than a statement about physical reality. Few realized that it would soon overturn the foundations of physics. What the Blackbody radiation problem ultimately revealed was the inadequacy of classical concepts at microscopic scales. It showed that ideas derived from everyday experience could not simply be extended indefinitely into the realm of atoms and radiation. The smooth glow of a heated object concealed a discrete underlying structure, invisible to the senses but decisive in its effects. This insight marked a turning point in scientific thought. The problem also demonstrated the power of experiment to guide theory. No matter how elegant or well established, a theory could not survive in conflict with clear empirical evidence. The Blackbody curves acted as an unyielding constraint, forcing physicists to adapt their thinking rather than adjust the data. This relationship between theory and experiment would become a defining feature of modern physics. In hindsight, the Blackbody radiation problem appears as the first clear signal of a new era. It exposed a boundary beyond which classical physics could not pass, yet at the time it was experienced as confusion and frustration rather than revelation. The revolutionary implications of its solution were not immediately recognized, even by those who contributed to it. The lesson of this episode extends beyond physics. It illustrates how scientific progress often begins with failure, not success. The inability of classical physics to explain Blackbody radiation was not a weakness, but a necessary step toward deeper understanding. By confronting a problem it could not solve, physics was forced to reinvent itself. The glow of a heated cavity, once a routine laboratory phenomenon, became a window into the quantum nature of reality. The Blackbody radiation problem transformed from an isolated technical issue into a cornerstone of modern science. It demonstrated that the most profound changes in knowledge often arise from the simplest questions, asked with enough precision to reveal the limits of what we think we know. The idea that energy could be divided into discrete packets was one of the most radical departures from classical physics ever proposed. For centuries, energy had been treated as a continuous quantity, capable of changing smoothly by any amount. This view aligned perfectly with everyday experience. Heat flows gradually, light appears as a continuous beam, and motion seems unbroken. Classical physics embedded this assumption deeply into its equations and concepts. Against this background, the introduction of energy quanta was not just a new idea, but a direct challenge to how nature itself was understood. The concept emerged not from philosophical speculation, but from necessity. Experimental results, especially those related to radiation emitted by hot objects, demanded an explanation that classical continuity could not provide. When attempts to describe these results failed repeatedly, it became clear that the problem lay not in mathematical technique, but in underlying assumptions. The continuous exchange of energy between matter and radiation led to predictions that contradicted reality. Something had to limit this exchange, and that limitation could not be expressed within classical rules. The solution appeared in the form of a simple but shocking assumption. Energy is exchanged in fixed, discrete amounts rather than flowing smoothly. These amounts were proportional to the frequency of the radiation involved. In practical terms, this meant that matter could not emit or absorb just any arbitrary amount of energy. Instead, it could do so only in specific chunks, later called quanta. This assumption imposed an immediate and effective restriction on high-frequency radiation, resolving the contradictions that had plagued earlier theories. At first, the idea of energy quanta was treated cautiously. It was introduced as a mathematical convenience, a way to make equations fit experimental data rather than a statement about physical reality. Even its originator regarded it as a temporary measure, not a fundamental principle. The notion that nature might operate in discrete steps seemed too extreme to accept outright. Continuity had been so successful in classical physics that abandoning it felt like surrendering reason itself. Yet the power of the quantum idea lay in its results. With this single assumption, theory aligned perfectly with observation. The infinite energies predicted by classical physics vanished, replaced by finite, realistic values. The radiation curves measured in laboratories emerged naturally from the calculations. This success could not be ignored. Even if the assumption felt uncomfortable, it worked where everything else had failed. The introduction of energy quanta also altered the relationship between matter and radiation. In classical physics, radiation was viewed purely as a wave phenomenon, spreading energy smoothly through space. The quantum idea suggested a more constrained interaction, one in which matter could only exchange energy in specific amounts. This hinted that radiation might possess particle-like properties, even though it clearly behaved like a wave in many situations. This duality challenged existing categories and blurred the line between waves and particles. The implications extended far beyond radiation. If energy exchange was quantized in one context, it might be quantized in others as well. This possibility raised profound questions about the structure of atoms and the stability of matter. Classical physics could not explain why atoms did not collapse or why they emitted light at specific frequencies. The idea of energy quanta offered a new way forward, suggesting that atomic systems might be governed by discrete energy levels rather than continuous motion. Acceptance of the quantum concept was slow and often reluctant. Many physicists viewed it as an artificial trick, useful but not fundamental. Others feared that it undermined determinism and predictability, key pillars of scientific explanation. Yet, as the idea was applied to new problems, its scope and necessity became increasingly clear. Each successful application strengthened the case that quantization was not an accident, but a fundamental feature of nature. The introduction of energy quanta marked a turning point in scientific thought. It represented the first clear break from classical continuity and opened the door to an entirely new framework for understanding reality. What began as a desperate attempt to solve a specific problem evolved into a principle that reshaped physics at its deepest level. Energy, once thought to flow endlessly and smoothly, was revealed to have an underlying granularity, hidden from everyday experience but decisive in the microscopic world. This moment did not immediately produce a complete theory of quantum physics, but it established the direction of change. It showed that nature could not be fully described by intuition alone, and that reality might be structured in ways that defy common sense. The introduction of energy quanta was the quiet beginning of a revolution, one that would transform science, technology, and our understanding of the universe itself. The appearance of a new constant in physics often signals a profound shift in understanding, and this was especially true in the case of Planck's constant. Before its introduction, the fundamental constants of nature, such as the speed of light or the gravitational constant, served as bridges between theory and measurement. Planck's constant played a different role. It did not simply scale known phenomena. It defined a boundary between two worlds, the familiar classical realm and a newly revealed microscopic domain governed by entirely different rules. Planck's constant emerged from the attempt to explain how energy is exchanged between matter and radiation. It linked the energy of a quantum directly to the frequency of the radiation involved, implying that higher frequency radiation carries larger packets of energy. This relationship imposed a strict structure on energy exchange. No matter how intense a radiation source became, it could not emit energy at a given frequency in smaller units than those defined by this constant. In this sense, Planck's constant introduced a minimum grain size for action in nature. What makes this constant remarkable is its smallness. Its numerical value is so tiny that quantum effects are usually invisible in everyday life. For macroscopic objects, the discrete nature of energy is effectively washed out, and classical physics emerges as an excellent approximation. This explains why classical ideas worked so well for so long. The quantum world was always there, but its influence was hidden beneath scales too small for direct perception. Planck's constant thus explains not only why quantum behavior exists, but also why it went unnoticed for centuries. The constant also carries deep conceptual meaning. It sets a fundamental limit on how precisely certain pairs of physical quantities can be known. While this implication was not immediately recognized, it later became central to the quantum description of nature. Planck's constant defines the scale at which uncertainty, probability, and discreteness replace determinism and continuity. It marks the point where classical intuition fails and a new kind of reasoning becomes necessary. In practical terms, Planck's constant determines the size of quantum effects in all systems. It governs the spacing of energy levels in atoms, the behavior of electrons in solids, and the interaction between light and matter. Without it, there would be no clear explanation for atomic spectra, no stable atoms, and no understanding of why materials conduct electricity the way they do. Every quantum phenomenon traces its origin back to this single number. The introduction of Planck's constant also changed the way physicists thought about physical laws. In classical physics, constants often appeared as parameters to be measured and refined. In quantum physics, this constant became a defining feature of reality itself. It is not something that can be derived from deeper principles, at least not yet. Instead, it stands as an empirical fact, a number that nature has chosen, shaping the structure of the universe at the smallest scales. Another striking aspect of Planck's constant is its universality. It applies equally to all forms of matter and radiation, regardless of composition or environment. Whether describing light emitted by a star, electrons bound in an atom, or vibrations in a crystal, the same constant governs the behavior. This universality reinforces the idea that quantum principles are not special cases, but fundamental laws of nature. Over time, Planck's constant became more than a parameter in equations. It became a symbol of the quantum revolution. Its presence in formulas serves as a reminder that classical descriptions are approximations, valid only when quantum effects are negligible. When this constant cannot be ignored, the world behaves in ways that challenge intuition, replacing certainty with probability and smooth motion with discrete transitions. The meaning of Planck's constant extends beyond physics into philosophy. It suggests that there are limits to what can be known and measured, not because of technological shortcomings, but because of the structure of reality itself. This idea represents a profound departure from classical thinking, which assumed that perfect knowledge was possible in principle. With the introduction of this constant, nature revealed that it operates with built-in constraints. Planck himself did not initially grasp the full significance of the constant that now bears his name. What began as a mathematical device gradually revealed its deeper meaning as quantum theory developed. Today, Planck's constant stands at the foundation of modern physics, quietly governing the behavior of the microscopic world. It represents the scale at which the universe transitions from the familiar to the strange, from certainty to probability, and from continuity to discreteness. When the new ideas that would later form quantum physics first appeared, they were met not with excitement, but with deep skepticism. The scientific community at the beginning of the 20th century was firmly grounded in classical thinking, and for good reason. Classical physics had delivered extraordinary success for more than 2 centuries, explaining motion, energy, and electromagnetic phenomena with impressive accuracy. Against this backdrop, the suggestion that energy behaved in discrete packets seemed not only unnecessary but intellectually disturbing. The resistance to quantum ideas was therefore not stubbornness alone. It was rooted in a strong and justified confidence in existing theory. Many physicists viewed the early quantum concepts as temporary fixes rather than genuine insights into nature. The introduction of discrete energy exchanges was seen as a mathematical trick, useful for matching experimental data, but not reflective of physical reality. Even those who introduced or used these ideas often did so reluctantly. They hoped that a deeper classical explanation would eventually emerge, restoring continuity and determinism. This hesitation slowed acceptance and shaped the cautious language used in early quantum research. One major source of resistance was the apparent conflict with determinism. Classical physics assumed that the future behavior of a system could be predicted exactly if its present state were known. Quantum ideas, by contrast, hinted at limitations in predictability and introduced elements of probability. This shift was unsettling. It challenged not only scientific habits, but philosophical beliefs about causality and order in nature. For many scientists, abandoning determinism felt like abandoning the very purpose of physical explanation. Another obstacle was the lack of a complete and coherent framework. Early quantum ideas appeared fragmented and ad hoc. They were introduced to solve specific problems rather than as part of a unified theory. Without a clear conceptual structure, it was difficult for physicists to see how these ideas fit together or why they should be taken seriously. Classical physics, by contrast, offered a unified picture that connected mechanics, thermodynamics, and electromagnetism under shared principles. The wave nature of light posed an additional challenge. Experiments in the 19th century had firmly established that light behaved as a wave, exhibiting interference and diffraction. The suggestion that light might also behave in a particle-like manner seemed contradictory. Many physicists found it impossible to reconcile these two descriptions. The idea that something could be both wave and particle defied common sense and strained existing categories of thought. Resistance also came from the success of classical approximations. In many practical situations, classical physics continued to produce accurate results. Engineers and experimentalists could rely on it with confidence. This practical effectiveness made it difficult to argue that a radical new framework was necessary. If classical physics worked so well most of the time, why replace it with something conceptually troubling and mathematically unfamiliar? Generational differences played a role as well. Senior physicists, whose careers and reputations were built on classical foundations, were often more skeptical of quantum ideas. Younger scientists, less invested in established frameworks, tended to be more open to radical change. This divide influenced debates, conferences, and the pace at which new ideas spread. Acceptance was not merely a matter of evidence, but of intellectual culture. Despite this resistance, quantum ideas continued to gain ground because they worked. Each successful application, whether explaining atomic spectra or photoelectric effects, weakened the case for purely classical explanations. Experimental evidence accumulated steadily, leaving less room for denial. What could not be explained away eventually had to be accepted, even if it remained uncomfortable. Over time, resistance shifted from outright rejection to reluctant adaptation. Physicists began to use quantum ideas pragmatically, applying them where necessary while avoiding deeper interpretive questions. This practical acceptance laid the groundwork for the development of a more complete theory. As mathematical formalisms improved and experimental confirmations multiplied, skepticism gradually gave way to cautious respect. The initial resistance to quantum ideas serves as a powerful reminder that scientific revolutions are rarely smooth. They involve uncertainty, disagreement, and emotional struggle as much as logic and data. The discomfort experienced by early 20th century physicists was a natural response to ideas that challenged deeply held assumptions about reality. In the end, the resistance did not stop the quantum revolution, but it shaped its path, forcing new ideas to prove themselves rigorously before earning acceptance. The true power of Max Planck's breakthrough became clear not through his own work alone, but through the profound influence it had on a new generation of physicists. What began as a cautious assumption about energy exchange soon inspired others to explore its deeper implications. These thinkers took the initial idea far beyond its original context, transforming it into a foundation for a completely new understanding of nature. The influence of Planck's work spread quickly, reshaping the questions physicists asked and the methods they used to answer them. One of the earliest and most important figures to recognize the potential of the quantum idea was Albert Einstein. While Planck had introduced energy quanta as a property of interaction between matter and radiation, Einstein took a bold step further. He proposed that light itself could behave as if it were made of discrete packets of energy. This idea allowed him to explain the photoelectric effect, a phenomenon in which light striking a metal surface causes electrons to be ejected. Classical wave theory could not account for the observed results, but the quantum interpretation matched experiments perfectly. Einstein's work gave the quantum concept a new level of credibility and demonstrated that it was not limited to a single problem. Niels Bohr extended these ideas into the structure of the atom. Classical physics could not explain why atoms emitted light at specific frequencies or why they were stable. Bohr introduced the idea that electrons could occupy only certain allowed energy states and could transition between them by emitting or absorbing quanta of energy. Although his model was still partly classical and contained inconsistencies, it successfully explained atomic spectra. More importantly, it showed how quantization could be applied to the internal structure of matter itself, not just to radiation. Other physicists quickly followed. The quantum idea influenced investigations into the specific heat of solids, where classical predictions again failed. By applying quantized energy levels to atomic vibrations, physicists were able to explain why heat capacities dropped at low temperatures. This success reinforced the growing sense that quantization was a universal principle rather than a special case solution. As these applications multiplied, the quantum concept began to reshape the language of physics. Energy levels, transitions, and probabilities replaced continuous trajectories and smooth flows. This shift did not happen easily. Many physicists struggled to visualize what these new ideas meant physically. Nevertheless, the mathematical results were compelling, and experimental confirmation continued to accumulate. The influence of Planck's work also extended to the development of entirely new theoretical frameworks. Inspired by the success of early quantum models, physicists began searching for a more consistent and complete description of microscopic phenomena. This effort eventually led to the formulation of quantum mechanics, a theory that abandoned classical notions of definite paths and introduced wave, functions, operators, and uncertainty as fundamental elements of reality. Importantly, Planck's influence was not limited to theory. The quantum ideas he helped initiate transformed experimental physics as well. New types of experiments were designed to probe atomic and subatomic behavior, guided by quantum predictions. The close interplay between theory and experiment became a defining feature of modern physics, accelerating progress and deepening understanding. Beyond individual discoveries, the quantum revolution changed the scientific mindset. It encouraged physicists to accept that nature might not conform to human intuition, and that mathematical consistency and experimental accuracy could outweigh visualizability. This shift in attitude allowed for more radical ideas to be explored without immediate rejection, fostering creativity and innovation. The legacy of Planck's influence is visible throughout modern science and technology. Concepts rooted in quantum theory underpin semiconductors, lasers, medical imaging, and emerging quantum technologies. None of these developments would have been possible without the chain reaction set in motion by the introduction of energy quanta. In this way, Max Planck's contribution extended far beyond a single problem or equation. By opening the door to quantization, he influenced Einstein, Bohr, and countless others, shaping the course of 20th century physics. The birth of quantum physics was not the work of one individual alone, but Planck's insight provided the spark that ignited a revolution, transforming how humanity understands the fundamental workings of the universe. The impact of Max Planck's work did not end with the development of quantum theory. It extended far into the future, reshaping science, technology, and human understanding in ways that continue today. What began as a cautious attempt to solve a specific problem evolved into a framework that underpins much of modern civilization. The lasting significance of this transformation lies not only in new equations, but in a fundamental change in how reality itself is perceived and explored. One of the most enduring effects of the quantum revolution is its role in defining modern physics. Quantum principles now form the foundation for understanding atoms, molecules, and subatomic particles. Without them, the structure of matter would remain mysterious. The stability of atoms, the arrangement of electrons, and the behavior of chemical bonds all rely on quantum ideas. Entire fields, including atomic physics, nuclear physics, and particle physics, trace their origins back to the concepts introduced at the birth of quantum theory. The influence of these ideas extends directly into everyday technology. Devices that are now considered ordinary depend on quantum behavior at their core. Semiconductors, which form the basis of computers and smartphones, rely on quantum energy levels within solids. Lasers, used in communication, medicine, and manufacturing, operate through controlled quantum transitions. Even modern imaging technologies and precise timekeeping systems are grounded in quantum principles. These applications demonstrate how abstract theoretical ideas can eventually shape practical tools that transform daily life. Beyond technology, the quantum revolution altered scientific methodology. It reinforced the idea that theories must be judged by their agreement with experiment, even when they challenge intuition. Classical physics had encouraged visual models and deterministic explanations. Quantum physics demanded a new kind of thinking, one that accepted probability, uncertainty, and mathematical abstraction as fundamental. This shift influenced not only physics but other sciences, encouraging openness to counterintuitive ideas when supported by evidence. The philosophical implications of quantum theory are equally lasting. The introduction of limits on measurement and predictability challenged long-held assumptions about objectivity and certainty. It raised questions about the role of observation in defining physical reality and about whether nature is inherently probabilistic. These questions continue to inspire debate among scientists and philosophers alike, showing that the impact of Planck's work reaches far beyond laboratories and equations. Education and scientific culture were also transformed. Quantum mechanics became a central part of scientific training, shaping how generations of physicists think and reason. The discipline developed new mathematical tools and conceptual frameworks, many of which later found applications in other areas of science and engineering. This intellectual legacy demonstrates how a single conceptual shift can influence the development of knowledge across multiple domains. The long-term impact of quantum physics is still unfolding. Emerging fields such as quantum computing and quantum communication promise to redefine information processing and security. These technologies exploit principles that once seemed purely theoretical, highlighting the unpredictable trajectory from fundamental research to revolutionary application. The seeds of these developments were planted when the classical view of energy was first questioned. Perhaps the most profound legacy of Planck's contribution is the lesson it offers about scientific progress. Breakthroughs often arise from confronting failure rather than celebrating success. The inability of classical physics to explain certain phenomena did not signal the end of understanding, but the beginning of deeper insight. Planck's willingness to consider an unconventional idea, even reluctantly, illustrates how progress can emerge from humility and persistence. In the broader story of human knowledge, the birth of quantum physics stands as a reminder that reality may be far stranger than intuition suggests. The universe revealed by quantum theory is not a smooth, predictable machine, but a dynamic system governed by probabilities and limits. This realization has reshaped humanity's view of its place in the cosmos. The lasting impact of Max Planck's work lies in this transformation of perspective. By opening the door to quantum physics, he helped redefine the boundaries of science and expanded the scope of what humans can understand and create. More than a century later, the effects of that moment continue to ripple outward, influencing how we explore the universe and how we imagine the future.